Okay, so off we go. We are going to pick up where we left off last time. We were talking about double integrals. And let's ask the next natural question. What happens if the domain is not a rectangle? Right? We've been making a fairly arbitrary choice so far of assuming that the only shape over which we would want to add stuff up would be a rectangle. And that, of course, in reality is not how the real world works. Okay, so here's a picture. Now you'll notice I'm coming at this from the graph point of view, again, as usual. So we're looking at some graph surface there. And now, again, with a non-rectangle base, right? Non-rectangular base like that, let's ask the question of how much volume is there. And we've, of course, asked this question for a rectangular base previously. And here's the good news. Pretty much everything goes forward exactly as it did before. So how do I compute this volume? Well, I'm going to slice up. I'm going to think of this as a loaf of bread. I'm going to slice it into slices of bread. The whole of the sum of the parts, right? That's no big deal. Any given slice of bread, well, there is a cross-sectional area. And that cross-sectional area, I can multiply by thickness. That cross-sectional area is an integral. The thickness is, again, still kind of like this. It represents a little piece of the y-axis, so that's dy, and it's just like we had before. Almost exactly. There's really only one little difference, and that is that, and then clean up my mess here. The one little difference is that this integral that represents the cross-sectional area, that integral has bounds. For example, let's think of the lower bound here, that move as y moves. So as you move across in this direction, as y, varies from C to D, you got these different cross sections. Some of these slices of bread are thinner, such as along in here, and some of these slices of bread are wider. Right? Or said differently, the range of values of x, such as here, x goes from sort of there to there, right? So there to there. But for a different value of y, let's suppose I looked instead at this value of y right there. Well, then the little slice of bread would be thinner. And so the x bounds as functions of y would be different. So that's the only difference. And algebraically, the way that looks like is whatever your, let's see, go into highlighter mode, whatever your inside integral is, the bounds will be functions of the outside variable. That's it. All right, so now how do we actually find those bounds? And, well, you can sort of look at the picture and work from there. Downside about this picture is it's hard to draw. It's three-dimensional. That's tough, right? It's just artistically challenging. So what I'm going to point out, first of all, I'm going to come back to several pages back here where we have this theorem that says that double integrals can be computed with iterated integrals. That's old news. We knew that. But notice in particular, the integrand for the double integral is the same as the integrand for the iterated integral. Right? So the integrand, we know. If we're interested in a double integral, we instantly know the integrand. It's the exact same for the iterated as for the original double. Okay, so looking at this situation, I know what f is, right? Anything that has to do with height, in other words. I already know what that is. If I want to know how these bounds vary over this domain, all I really need to know is the shape of the domain. Nothing more. And so what I'm going to do then is come down here. I'm going to take this picture, the same domain here as within the limits of my ability to draw anyway. Same domain. If I have a picture of that domain and I want to know these bounds, I can see those bounds in the two-dimensional picture. Don't need the three-dimensional picture. This is a huge savings in artistic workload, if you will. Now, okay, how do we, in this context, how do we actually in practice? Here we go. How do we figure out what those bounds are? There is a sort of a sequence of connections to be made that will resolve the matter. And here's how that works. Let's look at the lower bound here. This lower bound that I want, it represents specifically the x-coordinate of a certain point. So make sure to identify where that point is. Which point is it that represents the lowest value, as you sort of move along like that, which point is it that is that first point in that slice? That point is going to be on a particular curve. That curve, of course, will have an equation. Right? So this is the sequence. Whichever bound you're interested in corresponds to a point which is on a curve which has an equation. And all you have to do, keep in mind what we're interested in. I am interested in an x coordinate here. Right? This thing that I'm interested in is an x coordinate. So in that equation, just solve for x, and that'll tell you your bound. It's as simple as that. Right? So bound, point, curve, equation, solve. Let's see that in action. Okay, so here we go. Why don't I do this? That's nice. Okay, so we've got a domain that is a triangle with certain vertices given. So for this domain, defined by these three vertices, there, and there, and suppose I want to do a double integral. Now, real quick, before we get into the details here, where did this double integral come from? Doesn't matter. Maybe I'm computing the amount of mass distributed over this triangle. Perhaps. Maybe I'm computing the volume under a graph sitting over this triangle. Whatever. Wherever this double integral might have come from, I just want to talk about the sort of just the second phase of the process, namely how to turn the double integral into an iterated integral. And we're not going to worry about where the double integral came from or how to plug and chug. That's all stuff we know how to do. Okay. Okay, so all this noted. Let me clean up my picture. And here we go. Let's think about the range of values of x. Arbitrarily, no particular reason I'm doing dx on the outside. It doesn't matter. Okay, range of values of x. Well, here's my x slices. They look kind of like that. First one is there. Last one is here. Very often, when you're looking at outer bounds, it's pretty straightforward to just kind of look at the picture and see. Let's look at this lower bound here for x. Well, it's the origin. That was given. It's one of the vertices of the triangle. It's literally 0, 0. So what's the x coordinate at that point? Well, it's literally 0. And so lower bound, 0. Okay, what's the upper bound? The upper bound is going to come from looking at this edge. And you can think of that edge as being involved with either one of these points. Again, I'm looking specifically for an x coordinate. So take your pick. Doesn't matter. Any one of those, either one of those points, x is 1. So, boom. Everybody good? Alrighty. Now, we're going to fix a value of x. And now we ask, what is the range of values of y? So y is going to go from there to there. in particular representing sort of moving along my x slice from sort of there to there. And let's take this one step at a time. What's the lower bound here? Well, my lower bound for y corresponds to, lower bound for y corresponds to this point, which is on that curve, which has this equation. Now I want to recognize before I go on here, how did I know that this point was on this curve? There's 3 different sides of the triangle. How did I know which side to look at? And the answer is picture. Can't emphasize this enough. It's really important. In order to sort of make sense out of how to do these things, you need to have a picture. The picture will just show you, right, which one of the various curves you should be looking at. So in this case, the picture tells me it's that curve, y equals 0. Now let me remind myself here, why am I looking at this curve again? Right, it's easy to lose track and forget. Reminder, I'm looking for a y bound. So within this equation, I need to solve for y. Right? And what I get when I solve for y, that is my lower bound. So in this case, 0 is my lower bound for y. Everybody on board? Okay. Let's see here. Now, let me clean up the mess again. Get rid of all of this. Okay, and repeating. Now, let's ask what is the upper bound for y? Corresponds to this point, which is on that curve. Thank you, picture. Got to have the picture to make sense. How else would I know, right? The picture is what tells me. That curve has this equation. Now again, easy to lose track of what am I doing, where did this come from, why am I here, what am I looking for? Remind yourself at this stage, be sure to remind yourself, y is what I'm interested in. I'm looking for a y bound, so I need to solve for y in that equation. Now again, lucky break, it was already solved for. Sometimes you get lucky. You can't count on that. You will not always be so lucky. Right? But in this case, again, we were, and so sweet, and so our upper bound for y then is x. Everybody happy? All right. Cool. That's the process. We don't always drag it out so tediously. Right? Very often we'll be a little bit more sort of succinct with it. Here's another one that's still kind of dragging everything out. But let's walk through this. I'm going to move a little bit more quickly. Here I am going to do it in the other order. dx dy instead of dy dx. Let's see how that plays out. Right? And, well, let's see here. Y. This is what y slices look like. Right? As y goes from, over whatever range it is, right? And now we have to ask first and last. Okay, so the first y slice is sort of down here. Last y slice is right there. I think it's pretty clear from the picture that the lower bound for y is 0 and the upper bound for y is 1. Everybody buy it? Okay. All right, now, as usual, we fix a value of that outer variable. So we're going to fix a value of y. We are now going to ask what's the range of values of x, specifically as I go across that y slice. Right? So x is going to range from I don't know to I don't know for that value of y. Okay, play the game. What's my lowest value of y? Here's a landmine. A lot of students step on this particular landmine. What's the, sorry, I said y, I meant x. What's the lowest value of x, right? We're interested in x here. A lot of students will look and say, hey, the lowest value of x down here, x equals 0. And that's wrong. We are not interested in the overall lowest value of x. We're interested in the lowest value of x on our y slice. the fact that x becomes 0 down here is not relevant to what we're looking at, namely, what's the lowest value of x on our y slice. Now, you may think to yourself, well, yeah, but this point down here is part of our domain. I need to get that point. Don't worry, you will. You will get points down here for different values of y. For when y is lower, appropriate to where these points are down here, those lower values of y will get these lower values of x. Absolutely. So you're going to get them. But we're not just interested in the overall range of values of x. We're interested in how the range of values of x depends on y. And so we want only this point, not that down there. Everybody comfortable with that? Easy to mess that up. Okay, so that point, that line, that equation, again, really easy to get confused and forget what you're doing here. We are looking for x bounds, so I need to solve for x as a function of y. And the formula for x as a function of y here is y. That's my lower bound. Everybody happy? Okay. All right, and then likewise, the upper bound is 1. I'm going to let you all think through those details. Good little exercise. Let me hit the highlights real quick. Upper bound, that point, that curve, that equation. Why am I here? I'm looking for an x bound. We solve for x, and there it is. Just hitting the broad strokes there. Okay. Okie dokie. All righty, so either works. So how do you decide whether you should do it dy dx or dx dy? Right? Which one of these is better? In this case, I don't think it really matters much one way or the other. It's kind of whatever. It's pretty much the same. But sometimes it really will make a difference. And so you do, if possible, want to make some good choices. So I have some examples here that are designed to illustrate certain advantages that come up and how to notice them in advance. As early as possible. So here we go. Here we have a region that's defined by this equation and this equation. And notice it says here bounded by. D is the domain that's bounded by these two curves. This terminology means two things. It means that we're looking for one thing, for something whose boundary comes from those two curves. But we also need something that is literally bounded. Bounded means that you can put a fence around it. You can put it in a box. You can circle it. Right? It doesn't run off to infinity in any direction. And so specifically, the language bounded by is how you know that this is not the region that we were talking about. This sort of region up here would have the same two curves making up its boundary, but it is not bounded. Okay, so very careful with the language. That's part of the question, is to be able to interpret correctly. And D is this region in there. All right, and with that noted, let's slice it up. We're going to do it two different ways. Starting off, our outside bounds here, there to there. How am I going to know? How do I know where this starting point was for my x integral? Well, it corresponded to that point. That point is on a couple of different curves. It's on that curve, which has that equation, and it's on that curve, which has that equation. So the point that I'm looking for is on both of these. Quick reminder, note to self, I am looking for an x coordinate, right? I'm looking for the lower bound for x. So within this pair of equations, I need to solve for x. A lot of students will get this wrong and write down, oh, well, y equals 4, so boom, 4. Right? But that's not what we're interested in. We're interested in an x coordinate. So solve for x. Now you'll notice you get two different values of x when you solve that little bit of algebra. Plus 2 and minus 2. How do you know? Which one? Should it be minus 2 or plus 2? Picture. right? Your picture is your guide. It will point you right to what you want. And you can see from the picture here that we want, for this lower bound, we want -2. Everybody happy? Okay. For the upper bound, you're going to notice the upper bound here. Whoops. Oh, come on. There we go. This upper bound corresponds to that point, which is on the same two curves. Same algebra, same options. This time, clear from the picture. Again, thank you, picture, that I want the positive one. And so solving these for x gives me +2. Okay. All right. Now we fix an x. We now want to think about y. Y is going to go from, let's say, there to there, as I imagine this, moving along that x slice. And again, first and last, the first one comes from that point, which is on that curve, which has that equation. Now again, slow down, make sure you're clear what you're solving for. We're solving for y, because we're looking for a y bound. Again, lucky break, it was already solved for. So x squared. And then let's see, upper bound comes from this point, which is on that curve, which has that equation. Again, reminder, solving for y and 4. Everybody happy? Okay. All right. Okay, now let's do it again. Same question. I'm just going to slice it the other way, just because I can, right? Dx dy instead of dy dx. Same game, looking at our y bounds. If I slice perpendicular to the y-axis, I don't know, 0 to 4 kind of leaps off the page at you, right? It starts at the origin, and that's pretty clearly y equals 0. Ends on the line y equals 4. Pretty clear we're going to have y equals 4. So those bounds, kind of freebies. Now, as usual, we will fix a value of y. We will think now about the corresponding range of values of x, which, of course, let's see, the lower one is going to come from that point, which is on that curve, which has that equation, and here's the landmine. Here's where a lot of students blow it. Really importantly, really badly. A lot of students will look at this and say, okay, so x squared. And they'll make their lower bound here x squared. It doesn't make any sense. Because they forgot to remind themselves what they're doing, right? We are looking here for x bounds. So within this equation here, I need to solve for x specifically. Solving for x gives me an x coordinate, namely my lower x bound. And when you solve for x there, well, you're going to get a couple of options, either minus square root of y or plus square root of y. And again, you have to kind of think through which is it. Well, if I'm looking for my lower bound for x, clearly I want the negative one. And so minus square root of y here. Everybody happy? Yeah.
Just to understand fully, what would happen, like in the first case, we put like 0 on the lower bounds instead of x squared?
If you put 0 as the lower bound for x, like starting right here?
Where x squared is, if we put 0, what would happen?
Oh, I see what you're saying. Okay, let's go back up to that. So you're saying if you had mistakenly, thinking of y as, here's the lowest value of y. The lowest value of y is 0, and what would happen if you put a 0 there? Well, effectively then, you would have x going from -2 to 2, and then you would have y going from 0 to 4. And in effect, then, it's like your domain would actually be this whole rectangle. And that's just not what the right domain is. Yeah. Does that make sense? Yeah, okay. Cool. Is everybody happy with that? It's a good question. I appreciate that. That nice illustration of, what the problem is. Okay. All right. Okay, so here's our two options, and you can pick either one of these that you like. Now, I tell you, I have a pretty significant preference here. I do not like this one at all. X makes it look like it's wrong. Okay, I just don't like it. Right? And the reason I don't like it is because I don't like what's on the inside here. And the reason I don't like what's on the inside here is subtle. It's tempting to say, well, look at this inside integral. Yeah, nobody wants square roots, but that comes at the end. You plug those in after you've done the antiderivative with respect to x, and you could just plug in the square root and the minus square root and whatever. Who cares? And the reason we care is because while that inside integral is done, whatever we got there is going to be the integrand for my outside integral. That means that some form of ugliness with square roots plugged into it, some expression riddled with square roots, is what I'm going to be taking a y antiderivative of. And that sounds really bad, right? And y'all have flashbacks to Calc 2 classes, and integrals can be hard. And square roots are not a good thing in that area. All right. Okay, so natural, next question. Okay, so we're clear on which one we like better. How do I avoid this, and how do I ensure that I make a good choice that I'm going to be relatively happy with, like I did here? Okay, so how do I see this coming? And I have an answer for that. My little trick is to think about, well, okay, where did that square root come from? What made that square root show up? What made that square root show up is because of this x being on the inside, I had to solve for x. You can see it in the algebra that led to this. That square root of y literally came as I was solving for x. So look at your equation that you face. Ask yourself, which variable do you want to solve for? And I guess technically I can solve for either one, but if I had my choice, I'd much rather solve for y. Right? So because I would rather solve for y, I put dy on the inside. And because I don't want to have to solve for x, I do not want to put dx on the inside. That make sense? That's a good little pithy little observation to kind of keep in mind when you're trying to decide which way to slice. Look at the equations that describe your region and ask yourself, what do you want to solve for and what do you definitely not want to solve for? Okay, here's another we'll try it both ways and we'll infer a moral of the story. I'm going to go more quickly now with this sort of the slicing process because we've done several at this point. This triangle, same triangle, I can do it two different ways. There's dx dy, there's dy dx. The dx dy one, the bounds turn out to be this. I'm going to let y'all fill in the blanks on that. So just what we've done with previous examples. Y bounds, fix a value of y, then you look for x bounds. Let's see, I guess I could say it like this. Y goes from 0 to 1, and x goes from y to 2 minus y, and that's the details for y'all to fill in. Okay, here's the problem if I do it the other way. If I do dy dx, very first thing, we've got to think about the x range. And it's tempting to say x goes from 0 to 2, because it kind of does. But then we get a problem. Let's talk about the y bounds now, and let's talk specifically about the upper bound for y. As y goes from wherever it does to wherever it does, the upper bound for y, sometimes on that line, sometimes on that line. Those lines have different equations. When I solve for y to get an upper bound for y, I'm going to get different answers for different values of x. and you can't just stick in multiple things in there, right? It just doesn't work. So what you have to do here is break it up into first with x going from 0 to 1. Just looking at x being from 0 to 1, and then separately after have a completely separate consideration for x going from from 1 to 2. And with that being the case, no problem. My upper bound for y comes from this line. Details to be filled in. You get that value of x. That value for the upper bound for y. And then for the other values of x, the upper bound for y comes from that curve, in which you can solve for y and you get that upper bound for y. So it's not that you can't do it, right? We can make it work, but it's just kind of annoying that we have to cut this shape into half and sort of deal with each piece separately, and all else being equal, we don't really want to have to do that. Is that all good? Okay, so again, what's the moral of the story? How do we, when possible, if we possibly can, I'd really like to be able to avoid stuff. I don't want to do twice as much work. Right? So here's the way I like to think about it. The problem here was that the point giving my upper bound for y was on this curve, and then it became on this curve. That point that gave me my upper bound for y jumped from the one curve to the other. What made that possible? How could this point jump from the one to the other? It's because the curves intersected. And note that when curves intersect, they tend to make corners. Now, with these observations having been made, here's my pithy little rule. The pithy little rule is try not to slice through a corner. Because notice doing x slices, my x slices look like that, and there you go. I sliced through a corner. The fact that I put x on the outside is what made me slice through this corner, and that corner is why I have to stop the integral I had been developing, start a whole new integral to finish up the thing. Okay, so best, if at all possible, just try not to slice through corners. Again, this isn't, I'm not saying that you should never, ever, under any circumstances. Sometimes you can't avoid it. Sometimes, even though there's a cost to pay, sometimes there are other advantages to, doing it in a particular order, whatever. I mean, I grant that, there is no one size fits all. But good rule of thumb, try not to slice through corners. How are we doing? Yes?
So, like in the top example,
yeah,
we'd say that the slice through the corner is okay because it's like 0.
Yeah, well, that's right. So, let me say it differently. Anytime you slice through a corner, you're going to have to stop the integral you had been working on and start a new integral. So, quite right, yes, my y slicing, the very first slice, I sliced through a couple of corners. So, I'm going to have to stop what integral I had already been working on. I hadn't been working on one. I'm going to have to start a whole new integral. Cool. I wanted to start a new integral. And so, yeah, that's fine. And likewise, at the end, I hit another corner. I'm going to have to stop what I was working on. Good, I was done, right? So I guess I should say try not to slice through corners mid-process, right? And notice these sort of mid-process slices, no corners. Yeah. Okay. Okie dokie. So here's a last little annoyance I want to talk about before we move on. Sometimes the domain's not given. Okay, so for example, paraboloid, plane, volume in between, which I think is easier to see if we look at it sort of separately over here like this. And for every point in the shadow down here, every point in that shadow, I could imagine slicing up this shadow, right? For each little piece of the shadow, each little sort of chunk down here, there is a corresponding French fry, and I I make the accumulation argument, the grand total volume of this bowl of French fries is the sum of the volumes of the individual French fries, right? So the total volume is the sum of the individual volumes. So that's as usual, per normal, right? Nothing tricky there. I can also argue that each volume, let's do this orange. Each volume is going to be height times the area of the base, and the height is just the difference of these two z coordinates. So z2 minus z1 is my height. dA is the area of the base, the area of that little piece of purple little piece of the domain. That's all as normal, nothing weird yet. Here's the tricky part. It is not clear, it is not given in the statement of the question what this domain is. I mean, it's the shadow of my solid, but what's that? That's what I'm going to have to slice up, and I don't know what it is. Right? Okay, so the way I like to come at this is notice that if I look at, again, some arbitrary point in this region, for that arbitrary point there is what I'm going to call kind of a height up to the first surface, and then there is a height up to the second surface, the plane up there. There's a Z1 and a Z2, and again, blue minus green gives us the height of the French fry, blah, blah, blah. I make the case that what I'm interested in, the points that are on the boundary of my domain, the thing that's going to help me understand my domain there, are points where the height up to the lower surface and the height up to the higher surface are the same. Right? I'm interested in when the green is equal to the blue. Or said differently, I'm interested, right, in when this z and that z are equal to each other. And now let me zoom like this. Now there's a little bit of work to be done there if I want to set those z's equal to each other. And in particular, I'm going to have to solve for that z. It doesn't come pre-solved. Right, so a little bit of effort, solve for that z, and then setting the one equal to the other gives me that equals to that, and a little bit of algebra, yada, yada, yada. Notice the completing the square figures prominently in that algebra. You may recall, I've mentioned this before, completing the square, highly underappreciated in high school algebra courses. A little bit annoying, but it's got to be done. You really need to know how to do that. So make sure that you remind yourself or fill in that gap or what have you. Make sure you can complete the square. And then we're done. We have the equation of our, sort of the boundary of our domain. It's a circle, and now the slicing up of that domain just amounts to drawing a picture of that circle and playing the usual games. Everybody good? Okay. I have a warning. What I've seen many times, which is also completely wrong, a certain number of students will make the correct observation that I need the green to equal to the blue. They'll notice that the boundary down here comes from where these surfaces intersect, which is all good. And they will represent that the wrong way, though. Very common, surprisingly common. Students will represent these two surfaces as intersecting when that equals to that. Doesn't make any sense, right? There's no such thing as setting two equations equal to each other. I don't know what that's supposed to mean or where that's supposed to come from. You need to set the z's equal to each other because picture says so. Right? In the picture, it makes sense to look for points where the two heights are the same. That has a geometric basis. Setting one side of one equation equal to a different side of another equation, that doesn't make any sense at all. So please don't do that. Watch out for that. make sure to see the right way to do it. And if you have any questions about this, come talk to me in office hours. I'll be happy to show you what goes wrong and silly nonsense that can come about if you do it. If you make a mistaken argument like that. Okay. All right. Okay, so we're done with 5.2. We're going to be done with 5.3 in about a couple of minutes here. 5.3 is the shortest section in the book by quite a bit, at least in terms of what needs to be said. It's really only one example, not that much to it. It turns out sometimes, not even all that often, to be totally forthcoming, it's helpful to switch the order of the differentials from what you're given. Now, I'm going to walk you through real quick how to do that and why it might be helpful. The idea, though, if you have an integral, an iterated integral that is, where do iterated integrals come from? They come from double integrals. Double integrals defined on some domain. And you can just reverse engineer what this domain is. Notice the lower bound for x here is y. That corresponds to this curve here, x equals y. And notice that, the upper bound for x here is 1. That corresponds to the equation x equals 1. Right? And we're interested in what's going on in between those curves, between where y is between 0 and 1. And so what is it that's between the blue and the red for the orange values of y? And you can just see right here in the picture, then your domain is what I have shaded in gray, which I'm trying to shade in yellow, which doesn't really work very well. But that thing in between is our original domain. Is that cool? Okay, well, our original domain, once we've noticed our original domain, I suppose what we were asked to compute came from one slicing of that original domain. But how about this? Once I know the original domain, I can slice it in the other order if I want to. And that would give me this. Now, again, that's an exercise to think through how to, if you slice this shape here, this triangular shape with the differentials in the other order, then you get these bounds. Okay, so we've turned then one question, this dx dy iterated integral, we've turned it into a different question, this dy dx iterated integral. And by the way, you're going to notice, if you think back to various techniques that you learned back in single variable calculus classes, a lot of those techniques, let's take integration by parts, for example, it doesn't really solve your problem. It just turns one question into a different question. And sometimes being able to turn a question into a different question is valuable because sometimes the harder question turns into an easier question. And that's exactly what happens here. If you look back up at the original integral here, this original integral, the inside integral is, we can't do that. There is no, without using power series, there's no way to find an antiderivative for that function. And I would say give it a try, but that's mean. Because it's been proved you cannot do that. It does not work. On the other hand, this blue integral down here, perfectly doable. Now, a lot of people miss the convenience here. A lot of people look at this inside integral here and think, I see e to the x squared again. It's that same problematic integrand, but it's not the same because this is a dy integral, which means the variable further to the outside is constant. Let's see, where's my gray? Here it is. X is constant. That means this is not a function. It means e to the x squared is just a great big constant. And that's easy to integrate. And then when you finally get around to doing the outside integral is totally doable with an easy substitution. It's kind of awesome. So, nice little trick, a little slip move, right? And it's good to know that trick, and that's really kind of all that needs to be said about 5.3. So we just finished another book section, shortest section that we're going to be covering. And I'm going to move on now to triple integrals. I'm not going to be able to get very far into this, but I do want to lay some groundwork and float some ideas at you. What should be a triple integral? And I want to remind you where double integrals came from. Double integrals came from trying to reproduce single variable integrals. Okay, where did single variable integrals come from? We wanted to be able to get our hands on a certain category of questions involving quantities that accumulate, where the whole is the sum of the parts. Chop it up, add it up, right? And so Riemann sums were our foot in the door for single variable integrals. Chop it up, add it up. Double integral was just, let's hope that there are expressions where you can chop it up, add it up. We wrote down a 2-index Riemann sum, hoping that there would be quantities that accumulate over areas, which of course there are. So it's really the same thing here for triple integrals. The big idea of a triple integral is, look, I've got some solid region here, and on this solid region, maybe there are quantities where the whole is the sum of the parts. Well, of course there are. Mass, let's say, right? Maybe I've got a brick, right? And maybe the brick's not made out of a uniform kind of a clay. Maybe there's a denser clay on one side and then a lighter, more igneous kind of clay on the other side or something. I don't know any geology, something like that, right? And okay, well then, how would I compute the total mass in the brick? Well, the whole is the sum of the parts. Chop it up into little pieces. That's how mass works. It is intrinsically an accumulating quantity. Maybe this is a fish tank, and there's stuff floating. Maybe there's a ick floating in my fish tank, right? As I understand happens. And maybe there's more ick near the bottom and less ick near the top, right? And so, how much total ick is there in the fish tank? Well, chop it up into little pieces, and the amount of ick in each little box, you add that up over all the boxes, gives you total ick. Yeah? I mean, see how easy it is to come up. I swear I never thought of that until just now. Right? There's bazillions, countless examples of stuff that accumulates over solids. And so all we're going to do is say that, the whole is going to be the sum of the parts. And I just need to know that on each piece, in order to have something that I can kind of write down, and I do have to have a formula here, right? I'm going to talk about whatever it is my quantity that I'm interested in. That amount of stuff in a little piece needs to be something times volume. Something times size that fits with our pattern from double integrals and single integrals. It's stuff equals stuff per unit size times size. So in this case, stuff per unit volume times volume. Does that make sense to everybody? There is no particular quantity that we're thinking about as we write this down. It could be mass, it could be ick, it could be poison. Well, I don't know. Maybe I'm keeping track of how many pieces of bacteria there are floating in my fish tank. Whatever, it doesn't matter. This could be anything. But this expression is useful for just countless of these things. And so this expression deserves a name. It's a triple integral. It deserves a notation. I think the notation pretty much sells itself, right? And so that's what a triple integral is. A triple integral is a strategy for adding up accumulating quantities. And just because we're already here, how would I get my hands on the question of the amount of mass there is in this brick or whatever? The whole is the sum of the parts. Mass is an accumulating quantity. And then on each individual little piece, mass is mass per unit volume times volume. And therefore, mass can be computed with a triple integral. And that makes it a pretty good place to stop. We will draw the line right there. Y'all have a good break. See you on Wednesday. Yes?
If you're doing a triple integral over, I guess, like